Greeting everyone. We are a team from the database group at Tsinghua University and the supervision of Professor Guoliang Li. In this lecture, we study the problem of deep generative model for trajectory modeling and application. Over the course of our journey, we have tackled a multitude of challenges concerning big trajectory data, such as indexing, data cleaning, map matching, querying, and data mining on trajectory data. From our extensive experience, a critical lesson emerged. The precise map matching original trajectory data onto the pre-existing road network proved to be a more effective approach than working with raw trajectory data. Given the scalability of a road network, each trajectory can be elegantly represented as a sequence of IDs, with each ID corresponding a road network edge. This method allows us to capture the inherent pattern within the road network, resulting in a more refined expression of trajectories. Nonetheless, even when using map-matched trajectories, we encounter the following noteworthy concerns. Firstly, there is the issue of potential privacy breaches. In practice terms, spatial temporal trajectories handle sensitive personal travel information, and privacy regulation restricts the collection of such potentially risky trajectory data. Secondly, there is a substantial data preprocessing overhead. The rapid expansion and sheer volume of trajectory data result in preprocessing and maintenance costs that are extremely high, thus failing to align with the demand of lightweight analysis. Addressing the first concern, trajectory privacy protection method introduce noises into the probability distribution of the subsequent trajectory edge, aiming to safeguard privacy. However, this approach has the drawback of noise accumulation with trajectory lengths, leading to the reduced usability. As for the second challenge, even though trajectory data preprocessing has succeeded in reducing maintenance expense through techniques like compression and sampling, this method might potentially increase preprocessing cost or reduce the usability of the raw data. With the rise of a deep generative model, we found that it is possible to generate trajectory having the same distribution with the original data, which can solve the previously mentioned concerns. Our aim is to design a privacy-safe generative model, MT9, that supports both data generation and end-to-end analysis. On the one hand, under the premise of protecting privacy, it can guarantee trajectory sample of specific time and space range. On the other hand, it should directly support typical analysis tasks, such as frequent trajectory analysis, trajectory sequence prediction, and travel time estimation, while avoiding high data maintenance cost. Thus, we have the following three research objectives. Firstly, we need a lightweight model that supports data analysis to easily generate and analyze trajectory data. Secondly, we need a highly available model which accurately restores the distribution of historical trajectories and ensures the effectiveness of applications. Lastly, we need a privacy and security protection model which can guarantee privacy and security, avoiding sensitive data from being stolen. Based on the mentioned research objective, we have the following research challenges. First one is how to model trajectory data and the dependencies. Second one is how to describe a statistical distribution of high-dimensional inclined trajectory. Thirdly is how to avoid privacy leaks and support multitasking. Here, we showed the framework of MT-NIGHT. The input of MT-NIGHT include the departure session and the travel time. The model will gradually generate the current age and its transit time. The model component include trajectory representation model, road network knowledge encoding model, and trajectory prefix encoding model, and mental generator model to encode the map matched trajectory. The training phase input real sequence data, and the generation phase recursively inputs the current step to generate results. For the first challenge, we use a variance method to encode the spatial temporal feature since we observe that the trajectory distribution is closely related to road information, and the trajectory origins and destinations are more likely to be on residual roads, while trajectory route pass more high-level roads like primary roads. We use a road network age embedding and a time point embedding, as well as a road network knowledge embedding. For the second challenge, we use the following method to characterize high-dimensional tiled trajectory distribution. Firstly, we use trajectory prefix encoding. A typical LTSI is used to encode the embedding trajectory prefix to capture the long-term dependency of trajectory sequence. Secondly, we generate mental information. We design a mental learning model based on road network knowledge to match optimal network weight for different characteristic road sections. Finally, we use a trajectory suffix generation based on the mental learning generator. It can accurately describe the real generation description of the different road segment. To ensure privacy protection, we train the model with differential privacy with trim gradient and noises and include trajectory maximum likelihood loss and time-consuming absolutely error loss to ensure the generated trajectories are similar to the raw trajectory distribution while ensuring the privacy. Also, our model can support end-to-end analytic application. For example, given a trajectory and departure time, MT-NIGHT can analyze its frequency. The trajectory surface prediction task, including given a trajectory prefix, MT-NIGHT can predict its surface. And plus, given a trajectory path and a departure time, MT-NIGHT can estimate the travel time of the path. We also conducted experiments on trajectory datasets from the city of Chengdu and Xi'an from China. While they have very different trajectory distribution while similar road network complexity, we selected 3 baselines, NGRIME, AutoSTG, and CSSRNN. We use a distribution distance measure, GSD, to measure the effectiveness of these methods. We have the following observations. For the distribution distance, compared with space length, MT-NIGHT fits the original distribution with the smallest distance and the highest consistency. For the generation effect, the trajectory generated by MT-NIGHT is consistent with the original distribution, which can capture the thematic distribution law. For example, in the given heat map, the dark red part is high frequency, and we can see that the generated distribution is similar to the original trajectory distribution. For the task of frequent trajectory prediction, MT-NIGHT achieves over 4% greater accuracy compared to traditional approaches. For trajectory sequence prediction, MT-NIGHT shows an accuracy improvement exceeding 5% when compared to traditional methods. For estimating travel time, MT9 yield an error rate that is over 10 times lower than that of the traditional methods. To conclude, we propose a deep mental learning-based generative model named MT9 to support trajectory generation and analysis, meanwhile giving privacy guarantee. Secondly, extensive experiments showed that MT9 modeled real trajectory data with high utility, preserving original statistics and supporting real-world applications while keeping privacy. Thirdly, our future research direction include transferring learned trajectory generation pattern to neural network and adapt MT9 for new dataset. We appreciate your attention, and if you have an interest in our research, please explore our website to access our extensive collection of work on trajectory data. Additionally, you can make use of our publicly available code repos for more insight. Thank you.